All right, welcome, ladies and gentlemen, to the beginning of Chapter 5. So this right here is just an overview of what Chapter 5 is going to be. We're going to split this kind of into two parts here. The first part being the first four sections. This is what we call verifying trigonometric identities and also solving trigonometric equations. You're going to get a couple handouts from me, one being an identities page, cheat sheet if you would, and obviously your Chapter 5 assignment sheet. The last two sections here are actually solving triangles that are no longer right. So we're going to be getting out of the right triangle trigonometry and looking at how to solve triangles that don't have right angles in them. All right, so let's go ahead and look at what we're going to look at here today. The first section of Chapter 5 is what we call our fundamental identities. These are kind of the very first, very basic ones, the ones that we should memorize pretty quickly. Most of them are very easy to memorize. So some of the first basic identities that we deal with is what we call the reciprocal identities. We know a couple of them already. Like we know that cosecant is 1 over sine. And vice versa, the reciprocal of sine is 1 over cosecant. But some of the other ones that we don't know that you're going to see on your paper here is something like, actually the reciprocal identities we know. They are just the reciprocals of each other, right? The cosecant's the reciprocal of sine, sine's the reciprocal of cosecant. But the new ones, the quotient identities, this is for tangent and cotangent. Tangent is the ratio of sine divided by cosine. And this is pretty handy. And this is actually kind of something we've dealt with before. We remember that tangent on our unit circle, tangent of theta is equal to y over x. And we know that sine is the y, and we know that cosine is the x. So that should make sense if tangent is y over x. Therefore, tangent is actually sine over cosine. And this actually comes in handy when solving equations. We'll get to that after a while. And likewise, if tangent is sine over cosine, we know cotangent is the reciprocal, and therefore it's cosine over sine. Right now, I didn't really mention this. I'm really just kind of going through what they are before we go and use them. We're going to use them towards the end of this particular video. All right, so the first really, really big one would be what's called the Pythagorean identities. And you will think about the idea of the Pythagorean theorem. So we know that leg squared plus leg squared is equal to hypotenuse squared. If you think about your unit circle, and if you were to draw any triangle in there, every triangle has a right angle that we were dealing with in the last chapter. And we know that this is the x direction and this is the y direction. So our triangle has sides of x and y on it. And we know the hypotenuse is 1. Hence the word unit circle, right? So we know that each triangle can be written like this with the Pythagorean theorem. We know it's x squared plus y squared equals 1. And to go back to the last statement I made on the last page where I said that cosine of x is equal to, or actually cosine of theta is equal to the x coordinate and sine of theta is equal to the y, those two things actually go right into this identity. So we get our very first identity, our very first big identity, saying that cosine squared plus sine squared is equal to 1. All right, you need to know that these two things are exactly the same thing. So notice how here the square is on the cosine. It's around the whole cosine, but normally we write it like this, where it's the square is above the cosine. So this square does not go to the theta, but it goes to the cosine itself. Meaning, if I was to ask for the cosine of 30 degrees, we know that's root 3 over 2. But if I was to ask for the cosine squared, that would be this thing squared. So in this case, we would get 3 over 4. So cosine squared of 30 degrees is the square of root 3 over 2. Well, if we divided both sides of this equation, there's actually 3 Pythagorean identities. And they're all based off of this first one. This is our main one, the first one that you should really memorize. This is our first big one. All right, if we divided both sides by cosine squared, we get cosine squared divided by cosine squared. We know that's 1. And then we'd get sine squared divided by cosine squared. Well, we know from the previous page that sine over cosine is tangent, and therefore sine squared divided by cosine squared is tangent squared. And if we divided the 1 by cosine squared, we would get 1 over cosine, which is secant, and therefore we'd get secant squared. So this is the second of our 3 identities. I'm trying to just tell you guys where they come from. I'm going to give you a paper with all of these on there, but sometimes they're kind of hard to figure out where they came from. Lastly, if you were to also divide everything by sine, rather than divide it by cosine, if we took the original identity and divided by sine squared, you would get cotangent squared plus 1 is equal to cosecant squared. All right, so these are 3 very big, good identities, but they're all based off of the original. And again, we'll use them coming up. We're actually going to use them right here. So we're going to find sine and cosine if tangent is equal to 5. And we know that cosine is greater than 0. And that actually comes down to reminding us that if tangent is positive and cosine is positive, well, tangent is positive here and here, and cosine is positive here and here, we're looking at an answer in quadrant 1, which means sine will also be positive. All right, so the question is, how in the heck are we going to do this? Not really sure. We need to use our identities that we already know in order to solve for sine and cosine here. And we can actually think about a triangle if we really wanted to. But what we would try to do is try to get outside of the triangles. But let's just see what would happen if we had the triangle here. Tangent is 5, so that means it's 5 over 1. And that means this is the square root of, let's see, 25 plus 1, so 26. So we can figure out the cosine of theta pretty easy. It's 1 over radical 26. And sine theta is 5 over 26, root 26. But what if we wanted to try to do this without a triangle? Using just our identities, we know that tangent squared of theta plus 1 is equal to secant squared of theta. Now that doesn't really help me yet because I don't have sine and cosine, but we know tangent of theta is 5, therefore tangent squared is 25. So this tells me that secant squared theta is equal to 26, and therefore secant of theta is equal to the square root of 26. We know that cosine is positive, so therefore secant is also positive, so we don't care about the negative radical. Then we can say, because secant is root 26, cosine is the reciprocal of that answer, and sine, well, then I'd kind of use a triangle, but not necessarily needed. We could actually go cosine squared plus sine squared. Oh, no, let's not use that identity. Let's use tangent. We know that tangent of theta is equal to sine of theta over cosine of theta. In this particular case, tangent is 5, and cosine is 1 over radical 26. And if we multiply both sides by that denominator, we get that sine of theta is 5 over radical 26. 5 times this fraction of 1 over radical 26 is 5 over rad 26. Okay? That gives us these two answers, and yes, that is what we get with the triangle, but sometimes triangles don't really work. This particular case, it obviously would have. What about this one? I want to know tangent theta and cotangent theta if secant is 4. Now, this tells me that sine is less than 0, so we have to think about what quadrant we're dealing with. Secant is positive, which means cosine is positive, and that's in quadrants 1 and 4. Sine is negative. Well, sine is negative here and here, so we're looking at quadrant 4. So our answers have to correlate to quadrant 4. So here's what we're going to do. We know stuff about secant and tangent going together. We know that tangent squared plus 1 is equal to secant squared, just like we did a moment ago. So in this case, tangent squared theta is equal to secant squared. Well, that's going to be 16 minus the 1, minus 1 from both sides. So I get tangent of theta is equal to the square root of 15. Well, let's think about what is it. Is it positive or is it negative? Well, we're in quadrant 4. We know tangent is negative in quadrant 4, and therefore we have to do that. Well, that actually answers part of my question. The part of the question was, what is tangent? The other part of the question is, what is cotangent? Well, the cotangent is the reciprocal of the tangent function. So in this case, cotangent is just going to be negative 1 over radical 15. And obviously you're supposed to, cotangent theta. Obviously you're supposed to simplify your square roots, but we're going to leave it like that just to save on a little bit of time. All right, let's keep going here. We have another identity. We have a lot of identities today. Next one here we're going to deal with is what we call a cofunction identity. Remember back at the very beginning of our chapter 4, we dealt with sine of 30 and cosine of 60. We noticed that this is equal to a half, but so is this. And at some point in time, I mentioned that 30 plus 60 is 90, which means 30 and 60 are complementary angles. Well, complementary angles have an identity to go along with them. Okay, so what I'm just saying here. If you have the sine of pi halves minus theta, well, that doesn't really sound right. So if I did the sine of 90 minus 60, it's going to equal the cosine of 60. Does that make sense here? Okay, so let's see that. 90 minus 60 is 30, and cosine of 60. We know that those two things are the same because we just decided that, or we just said that just a second ago, if theta was 60 degrees. So two complementary angles can be written in such a way. So if we had sine of pi halves minus theta, it's equal to cosine of theta. And you'll see when you get your paper that there's actually two more. There's two more cofunction identities, at least for the cosecant and for the tangent versions. All right, another identity here. We've dealt with even and odd functions before, so we have to remember that sine, cosine, and tangent and the other three can be even or odd, and they actually are. The only even function that we have is cosine. And cosine is the only function, cosine and secant, because they go together here. Cosine and secant are both even functions. So cosine of negative x is equal to cosine of x. So I'll write in here. And secant of negative x is secant of x. And the other four functions are all odd. And an odd function looks like this. If you plug in a negative value, you get out the opposite of the original function. So sine of negative x is negative sine of x. This actually could come in handy for graphing. In past years, I've given a very hard graphing question where we actually reflected a function over the y-axis. If you recall, f of negative x actually is a reflection over the y-axis. It changes all of my x's to negative or positive. So if I was to give you, come on here, if I was to give you, there we go, a function that would look like this, tangent of pi thirds minus x plus 2. Well, we never graphed any of these in this particular class, but in previous years I have. And this right here, because the negative in front of the x, it tells me to reflect across the y-axis. But this became too much of a challenging problem. I've recently just taken it out. But what we can do is we can factor out a -1 out of this inside piece, so we get the normal look of x minus pi thirds. But we know from the even and odd identities that the tangent of a negative something is equal to the negative tangent of that something. So that actually shows that this minus x, even though it's a reflection in the y-axis, since this is an odd function, it also is a reflection in the x-axis. And that's that statement that I just made there. Okay, so that could be handy if you had a problem like that and you didn't like the look of pi thirds minus x. You could actually rewrite it using your even and odd identity to make it look like the x minus pi thirds. All right, so now let's go ahead and use some of these identities here. If cosine of theta is equal to 0.34, we want to be able to find sine of theta minus pi halves. So here's what we're going to do. We know that sine of theta minus pi halves can be rewritten as negative sine of pi halves minus theta, using the same logic as we used on the last page. Because sine is an odd function, we can factor out the negative, and the negative actually fully comes out to the front of sine. Now, using our cofunction identity, we know that the sine of pi halves minus theta is actually equal to the cosine of theta. And we know what cosine of theta is. That's 0.34, so negative cosine is just negative 0.34, and that's our final answer. We didn't use a calculator, we didn't use any graphing. All we did was use our identities to show what that answer is going to be. All right, moving right along. This is where things start getting good. We're going to use all of our identities, at least the ones we've learned today. We're going to use these identities to simplify trigonometric expressions. This is where it gets good. What we need to do is we need to do algebra on this stuff. Now here's what you have to understand. That equal signs that I just wrote is an equivalence statement. It doesn't mean it equals anything where we solve for x. You cannot solve for x here. There's nothing you can solve for. But we can do a lot of our algebra that we already know how to do. If this was x cubed plus xy squared, I know both of these terms have an x in them, so I can factor out an x. I would then get x squared plus y squared. Now that would actually be it if we were just dealing with algebra. But let's say we had this function, this statement actually. Sine cubed and sine, they both have a sine function in them, so I'm going to factor out a sine of x. When I factor out a sine of x, I get sine squared x plus cosine squared x. So it follows along just like the algebraic expression above. Then we use our identities to simplify this if we can. Well, we know that sine squared plus cosine squared is 1, and 1 times sine is just sine. So this big, ugly expression simplifies down to a simple sine of x. Which means if I was to ask you to graph this big, ugly thing, which I'm not going to, but if I was, you could actually use your identities to simplify the function down to sine of x, and that is actually all you would have to graph. What about something like this? We have the secant x plus 1 times secant x minus 1 all over sine squared x. So whenever I see something like this, I just want to FOIL. All right, so secant times secant is secant squared x. Okay, so I have a plus 1 secant and a minus 1 secant, so I get 0. And I get 1 times negative 1, which is negative 1. Okay, well, we have an identity that says something about secant squareds and 1s in them. We know that tangent squared x plus 1 is equal to secant squared x, which means if I was to subtract 1 from both sides, that means tangent squared x is equal to secant squared x minus 1, which means I can replace this numerator with tangent squared. So now I get tangent squared over sine squared. All right, well, that's not simple enough for me. I know that tangent is sine squared x over cosine squared x. And I'm dividing by sine squared x. I'm taking tangent squared divided by sine squared. Well, this is sine squared x over cosine squared x for the tangent times 1 over sine squared, right? Dividing means I can change it to the reciprocal. Sine squareds cancel. I have to go back this way because I didn't leave myself enough room. I get 1 over cosine squared. And 1 over cosine squared is secant squared x. So again, this big ugly thing just becomes secant squared x. All right, I think I have one more on this page here. I do. All right, I purposely give this problem because nobody likes fractions. All right, from looking at this, I can't actually do anything to it. However, I have two fractions and I can create common denominators. Well, the common denominator here is just going to be the product of the two. So here I'm going to multiply by 1 minus sine of x and 1 minus sine of x. And here I'm going to multiply by cosine of x and cosine of x. So on the left fraction, I get cosine squared. And because they have common denominators, now I'm going to go ahead and combine. This becomes a minus sine times 1, so it's a minus sine of x. And a minus sine times another minus sine because plus sine squared of x. All over cosine x times 1 minus sine of x. Well, that kind of looks more complicated than it needs to be, so let's see what I can do. Here I have a cosine squared plus sine squared, and the commutative property tells me I can add these in any order that I would like, and cosine squared plus sine squared is 1, so now I have 1 minus sine of x over cosine x times 1 minus sine x. Well, now I have the same thing in the numerator and denominator, which gives me 1 over cosine, and I know that to be secant of x. And that would be my simplified version. All right, so I said at the very beginning that we are verifying identities and simplifying using identities, but we're also going to be solving equations. So we're going to need a lot of our chapter 4 that we dealt with where we were trying to find x's or trying to find angles, and that's what we're going to be solving for. So we're looking for all answers to this equation. So now we have an equation, so we have to work with both sides of the equal sign. The question is, how are we going to do it? First and foremost, do not try to multiply both sides by a function or divide both sides by a function. That usually is going to mess you up a little bit. Let's just first deal with this being cosine cubed x over sine of x equals, well, cotangent, I don't like cotangent. I kind of want to see it as a cosine x over sine of x. Just as with normal equations, we like to set it equal to 0 because they're usually easier to solve. So let's subtract both sides. by cosine x over sine of x. So I get cosine cubed minus cosine x. They have common denominators, so that's kind of nice. Makes it equal to 0. Now, if a fraction is equal to 0, that means the numerator is equal to 0. So I can say cosine cubed x minus cosine x is 0. I could then factor and from this I can factor some more actually. If you remember your algebra 2, something squared minus 1 becomes that something plus 1 and that something minus 1. And this is super nice now because we have a product of three things that equals 0. That tells me that cosine of x has to be 0. Cosine x plus 1 is 0, so I'm going to say that means that cosine of x is equal to negative 1. And here this one tells me that cosine of x is equal to 1. But that's not what we're trying to solve for. We're trying to solve for the angles that make this true. And because I say 0 to 2 pi, that means my answer has to be in radians. All right, so if we look at cosine, we know cosine is 0 at, oops, sorry, not 0. What am I doing? I have an eraser. Let's go, that's sine. So cosine is 0 at pi halves and 3 pi halves. Cosine is negative 1 at pi, and cosine is positive 1 at 0. Yes, it's also positive 1 at 2 pi, but we're going to not include it because that would be answering the same thing as 0. So there, look at there, we've got 4 answers to our equation. All 4 of these answers will give us a true statement in the original equation. All right, I have one more for us. I have 2 sine squared plus sine x equals 1. What you need to think about is all of your knowledge that you have about quadratic functions. Because this really is a quadratic style of equation. We always set them equal to 0 and then we factor. It follows exactly like your algebra, except for we have to throw an extra step at the end where we're actually trying to solve for x, not just sine of x. All right, so this first one tells me that sine of x is equal to plus 1 over 2. And here this one tells me that sine of x is equal to negative 1. And if we look on our circle, remember that's what we're actually doing here. We're looking at our circle. What value gives sine of x equal to positive half? And we know that is at pi sixths and 5 pi sixths. And sine is negative 1 at 3 pi halves, and that is all she wrote. That's our 3 answers. You could get 3 answers, you could get 1 answer, you get no answers, 10 answers, 8 answers. There's all sorts of different types of answers that you can get in these particular problems. Here's your assignment. Since you guys don't have your assignment sheet, you actually should probably get this started before coming. And I'll explain things when you guys come see me tomorrow. I hope you guys learned a lot. I'll see you later.